All right, it's 2, so let's get started. Um, so just to let you know how the rest of this week's gonna go out. So we have a little more to cover from Friday's lecture, and what we cover will be on test 4. So the rest of this lecture will be on test 4. When we go to our new lecture that I have prepared for today, that will not be on test 4, which is Friday. That will appear on the final exam, that information. Um, so that will be the only new information for the final exam. And we won't finish all that today, probably. So the idea for Wednesday is to finish whatever we have left. And then I'm willing to take any questions on test 4. Also, next week is your study period for reading days that the university gives you. So if you want to set up something for the final exam, like study for it and have me along, let me know. I might also put up like a poll to see if there's a specific time that a majority of people want to have like a final exam Zoom meeting where I can answer questions. We can definitely do that as well. So just let me know and we can work it out from there. Otherwise, let's look at the few remaining slides from Friday. Just to remind you what we've been talking about, we've been looking at Michaelis-Menten reactions and the kinetics of that. So all the math and kinetics with enzyme reactions. The last few slides are looking at the different ways a molecule can react with an enzyme. Excuse me, I had to sneeze there. So what we're going to be looking at is different ways a bisubstrate reaction can happen. So first off, what is a bisubstrate reaction? And a bisubstrate reaction is a reaction that uses two substrates. The majority of enzymes use bisubstrates. They have two substrates in their reactions. In the Michaelis-Menten kinetics we have been talking about, we've only talked about one substrate. So we're complicating things a little bit here, but lucky for y'all, I'm not going to ask you to do the math on bisubstrates. Rather, we're just going to look at the different ways they can occur. And when we look at mechanisms for bisubstrate reactions, they usually happen in like one of a few ways. So the first way we're going to look at a reaction mechanism is called a sequential reaction. And a sequential reaction is that before any chemistry can happen, both substrates have to be bound to the enzyme. And there's two ways this can happen, as I'm showing here on this PowerPoint. You can have an ordered sequential reaction or a random sequential reaction. And the word ordered and random here, that just means how your substrates bind. If your substrates have to bind in a particular order, for example, on the left here, we have substrate A binding to our enzyme E to make the EA complex. Then after A has been bound, only then can B bound to make EAB. Once you have both substrates bound, you can make your products P and Q. And so they come on in an ordered way and they come off in an ordered way. So P comes off and then Q comes off to get our final enzyme. Or you can have a random bisubstrate reaction. That's when it doesn't matter what comes on first. A can come on first or B can come on first. All that matters is that both substrates are there before the reaction happens, which is this middle part there. So just a few things for you to know there. know what a sequential reaction means, know what an ordered sequential reaction is, and know what a random sequential reaction is. And the other type of reaction, other than sequential, it's called a displacement reaction or a double displacement reaction or ping pong. And what a ping pong reaction is that you bind one substrate and then you release a product. When you release the product, you change your enzyme. And that's what we're showing here, right? So we have enzyme E that's being bound by substrate A to get the EA complex. Once you have the EA complex, chemistry happens to make your product, P. And when that chemistry happens, you fundamentally change enzyme E to enzyme F. And let's imagine the ways this can be done. So let's say we do some reaction and I don't know, we're doing a decarboxylation reaction. So let me draw a super simple molecule here. So let's say we have a reaction CH3, C double bond O, that works. Yeah. Very, very simple molecule. And let's say in our product, we're just going to make methane. And so this carbon dioxide, when we do this reaction, could be stuck to our enzyme, right? So the reaction could be from our molecule here. We take our carbon dioxide molecule and stick it onto our enzyme. This is what we mean by like enzyme F, and that we've changed the enzyme. It gets some molecule added or some functional group taken away to change it. Now, with enzyme F, then a molecule B could come in. This B can bind to F now because it has our new functional group or functional group taken away, do some chemistry and become Q. When we go from B to Q, molecule B to molecule Q, we do that in such a way to reverse what we did here. So we either give back the functional group or we add back the functional group we lost in the first step to go back to enzyme E. So going to my example here, if this process happened from molecule A to going from molecule P, then what would happen if we had our enzyme plus functional group and we add in B? Well, maybe we add the functional group to molecule B and we call this Q because it's a different molecule. Remember, we were calling this F. And so we go back to E without any carboxyl group, so that's good. And we make something else, Q, which is just B with our carboxyl group there. So that's an example of what double displacement or ping pong means. And when trying to figure out if your enzyme does sequential or ping pong, you can only really do that through experimentation. You can't just look at an enzyme and figure it out. You have to do some experiments to do that. But are there questions about the sequential method versus the ping pong method? And if you're wondering why it's called ping pong, ping is going on, pong's going off. So ping pong, right? Whoever said scientists don't have a sense of humor. All right. So let's see if we understand the ping pong mechanism then. So I have a bisubstrate reaction and I add P. and I label P with some marker that I can find. So isotopically labeled, that just means I add a molecule that is more or less radioactive that I can follow. So I have radioactive P. And I also add A. And I have E as well. I do not have B. And I do not have Q. If my enzyme follows the ping pong mechanism, will I eventually get this A to be labeled? Think that over. Take like a 45 seconds to a minute. Think to yourself, based on the situation I just had here, will we have labeled A? So this is a good way to see if you understand what ping pong means. And yeah, that's basically the point of this question. So I'll give you like 30 seconds to a minute to think about this. Okay, so hopefully you've come to some kind of answer on your own there. So one thing that you need to remember for enzymes is that enzymes work in reverse. So if A can go to P, then P could go back to A, right? So that is possible. However, this would only work if you have the enzyme version F around. So if you look in our reaction, we only have E, A, and P around, no F. So based on what I just said there, you might think, oh, okay, I can't go backwards, because let me draw this out. So going this way, you need enzyme version F. While going this way, you need enzyme version E. And let me just flush out the rest of the chart there. So if I was doing this, I need F. Going this way, I also need F. Going reverse, I need E. So this is the basic ping pong right here. So from that information, you might think, oh, so it's impossible. I can't get A. However, I will tell you it is possible because you have both E and A to begin with. And what will happen is that this E and A will combine to make F plus P. Once you make F, this F can interact with the labeled P you have to begin with and go backwards to make E plus labeled A. So based on the ping pong method, it is possible in this setup, given on this problem, to create labeled A based on what I just said right there. Any questions about that logic, or did I lose you, or anything at all about this idea here? All right. Now I have another question. Let me clear that. Along the same lines. This time, I have a bisubstrate reaction. And I add P that is labeled. And also the first substrate A and E as well. I don't have B or Q. So let me write that down. So I have labeled P, and I have enzyme E, and I have substrate A. I don't have B, I don't have Q. Will it be possible for A to be labeled if I have a sequential mechanism? And assume that you can either be ordered or random. Either one of those will be possible to make labeled A. Again, let me give you like a minute to think about this. And based on how we handled the last question, let's see if you can logic out how to handle this question. I'll give you time to think about that. And if you have questions, feel free to let me know. All right, so let me do the same type of idea here that we did for the for the ping pong mechanism. So if I want to go to here, you need enzyme E and A already. Here you need E, A, B. One sec. All right. So there's those forward reactions. And to go to Q, right? So P comes off, and so this would be EQ, which is already labeled to go there. Now, if I look at this mechanism, I have E, A, and P. And let's do reverse. If I want to go reverse, I need E, P, Q. Go reverse here, E, B. And to go reverse here, I just need E, Q as well. So there's no way I can actually go reverse or forward in this mechanism. And it works out the same with a random. So I have EA, and I can bind those to make the EA complex, but I don't have any B. So I can't go on and make P or Q. Well, let's look at P star, right? So I have P labeled, but I don't have Q. So I can't go backwards and make B or A because I don't have both products. And I can never make Q because I don't have B to start with. So in a sequential mechanism, you need both reactants to make a product. Or if you want to go backwards, you need both products to make your reactant. So if I don't start with both reactants or both products, there's no way my mechanism, my reaction would ever happen. And so this is no. It would not become labeled. Any questions about that idea or mechanisms or anything at all that you might have? Any confusions? Any place where I lost you? Anything that I spoke too fast and you didn't copy down? All right, let me switch PowerPoints then. This PowerPoint that I'm about to put up, it's going to be found in the folder I just created today, which is called Final Exam New Information. And the last topic for biochemistry 1 that is, that we're going to talk about is inhibition. That is how to stop an enzyme from working. So we're just going to start with some vocab. First, inhibitor. An inhibitor is something that reduces an enzyme's activity. It slows it down, basically. An inhibitor is, well, let me just say, an inactivator kills an enzyme, right? It makes it so the enzyme can never work again. So not all inhibitors are inactivators, though. But an activator completely shuts down the inhibitor. And you have different types of inhibitors, and we classify them based on where they work. And the first one we're going to talk about is called the competitive inhibitor. And what a competitive inhibitor does is that it binds at the same site as your substrate. So that's why I'm saying compete with substrate at normal binding site. It will try to bind at that same exact place. Therefore, if I'm trying to bind at the same exact place, it makes sense that I look just like my substrate. So yeah, that sentence doesn't make sense. Usually resembles the inhibitor. Usually resembles the substrate. And there's two ways you can do it. One, if you look like the substrate, or an inhibitor that happens naturally in your body is called product inhibition, where you have so much product around, this will go and bind the active site and stop the reaction. This happens in your body all the time, especially for metabolism. And if you are interested in metabolism, Biochem 2 offered in the spring. So the way we slow down metabolism is if you like ate a big meal and you have a lot of glucose, you're going to be burning this glucose through glycolysis. And one of the things after glycolysis in the citric acid cycle that you make is called citrate. What citrate can do is it can go back to your glycolysis enzymes and bind those enzymes. So you no longer do glycolysis, and instead you store that glucose usually as fat or glycogen. So that would be product inhibition, where the product can go and inhibit the enzyme. To make a really good competitive inhibitor, you want to make what is called a transition state analog. And a transition state analog is a molecule that looks just like the transition state and will bind to your enzyme and kill it. And here we have an example of competitive inhibitor for succinate dehydrogenase. Succinate dehydrogenase is part of the Krebs cycle, and it's also complex 2 in the oxidative phosphorylation chain. And what it does is that it changes succinate, shown here, to fumarate. Well, malonate looks a lot like succinate, and malonate will go and bind to succinate dehydrogenase and make no reaction happen.
Another type of inhibitor, Tamiflu here, where it can interact with a molecule in the liver. And when it binds, it will actually make ethanol. So Tamiflu will get you drunk. And it'll go and interact with that enzyme in your liver to do that. So just so we understand the concept of what a competitive inhibitor would look like, if molecule A is our substrate, which one is more likely to be a competitive inhibitor, B or C? I'll give you like 10 seconds to think about that in your head. All right, that's about 10 seconds based on my counting. I didn't do the Mississippi method. I just counted on my fingers. That would be B. So B looks a lot like A. C is a little too different in that this big phenyl ring would probably not bind as well as B. Any of you who have dreams of going to pharma school, this is a massive idea of drug discovery. If you know what the transition state looks like or the substrate, you just make a drug that kind of looks like that, but maybe has one more methyl group or a methyl instead of a carboxyl group. You have just made a drug that inhibits an enzyme. So that is the basis of drug discovery, this competitive inhibition, or probably the most common type of drug that infects or interacts with an enzyme is a competitive inhibitor. So let's look at the math of competitive enzyme inhibition. And a new mathematical variable we're going to bring into our discussion from last week is Ki. Ki is called the inhibition constant. And it's just a number that tells us how good a molecule is at being an inhibitor, where the smaller number equals a stronger binding. And we can understand that because this is the formula for an inhibitor. If you don't remember your variables for the Michaelis-Menten equation, this E is free enzyme. This I is free inhibitor. Remember, brackets mean concentration. So concentration of free enzyme, free inhibitor. And this EI is the enzyme inhibitor complex. So if you have a small number, that means that the denominator is big. If the denominator is big compared to the numerator, that means you have a lot of enzyme inhibitor complex, not much free inhibitor, not much free enzyme. So Ki will be a very small number. So just keep that in mind. The smaller the Ki, the stronger the binding. Now, the thing that a competitive inhibitor does is that it doesn't change Vmax. No change to Vmax of an enzyme. But instead, it increases Km. And let's think about why this is. If we look at our Michaelis-Menten outline or reaction outline, let me erase that line. That's not supposed to be there. So last week we talked about Michaelis-Menten, enzyme plus substrate goes to complex, makes product plus free enzyme. The way the inhibitor works, the competitive inhibitor, is that it binds the free enzyme to make our enzyme inhibitor complex, and then no reaction happens. So let's think about why Vmax and Km change the way they do. So we said Vmax doesn't change. And the reason why Vmax doesn't change, which is the maximum speed your enzyme can go, is because your substrate can always outcompete your inhibitor. If you add, 5,000 substrate molecules for every one inhibitor molecule, your inhibitor will never bind. You just have too much substrate, and your substrate will outcompete your inhibitor. So you'll be able to go your maximum speed regardless of inhibition. However, Km increases. Remember, Km is the substrate concentration to go 1/2 Vmax. And this is probably like the 10th time I've said that. So don't be shocked when you see a question asking something like that. Hint, hint, nudge, nudge, wink, wink. So that's the substrate I need to go to 1/2 my maximum speed. If I'm competing with something, I need more substrate to reach that goal. Because now it's just not me and the enzyme alone. I have this inhibitor that's trying to get with my enzyme. And I don't want that to happen. So I need more and more substrate to bind to my enzyme now. So the way your Michaelis-Menten equation changes for initial velocity, remember V naught is initial velocity, is that you have Vmax times substrate divided by this alpha constant, Km plus F. This alpha is like, I don't have a good word for it, but it's due to inhibition. The higher this alpha version is, this alpha number is, the better an inhibitor you have. Because if alpha is 2, you're saying you need twice as much substrate to go 1/2 your maximum velocity. And one way we call this is Km apparent. So alpha Km, another way that people will list this as is your apparent Km. It's the Km you're measuring when you have an inhibitor. And finally, we can put a mathematical formula to this alpha number. It is 1 plus free inhibitor divided by Ki, your inhibition constant. So there's ways we can calculate alpha, and then we'll know how much Km changes. So that was a lot of me talking there. So let me take a pause there and let you organize your thoughts, catch up. But any questions about our competitive inhibitor? All right, if not, we can move on. How does a competitive inhibition, or how does competitive inhibition look on a Lineweaver-Burke plot? So let's just remind ourselves what a Lineweaver-Burke is. It's also called a double reciprocal plot, where on the y-axis is 1 over velocity, and the x-axis, it's not showing up there, is 1 over substrate. So remember, alpha is inhibitor. The bigger the alpha, the better the inhibitor. So this green line is no inhibitor, blue and purple are inhibitors. And we said Vmax doesn't change. So remember, the y-intercept is 1 over Vmax. No matter what type of competitive inhibitor you have, Vmax doesn't change. So all your inhibitor lines will cross at the y-axis. And remember, the x-axis is 1 over alpha Km, negative 1 over alpha Km. So the way to know if you have a competitive inhibitor is if all your lines cross at the y, but they don't cross at the x. And the stronger the inhibitor is, the closer it will go to 0. And we can make sense of why it gets closer to 0. So let's make it easy on ourselves. Let's say Km is 1. And in the no inhibitor case, alpha is 1. So this green line, it would cross at the x-intercept at 1 over 1 times 1, because alpha is 1, Km is 1, negative. So it will cross at -1. If alpha is 2, it will cross at -1 divided by 2, which is alpha, times 1, which is -1/2. If alpha is 4, as given in that example, it will cross at -1 divided by 4 times 1, or -1/4. And if it's been a while since you've done fractions, let me just write out the values for you. So the stronger your competitive inhibitor, the closer it'll get to the y-axis. All right, so questions on the Lineweaver-Burke with competitive inhibitor. All right. And that brings us to our next inhibitor type, and I'm just going to write down what it says down here. That is uncompetitive. Our inhibition constant here is Ki prime. And what an uncompetitive inhibitor does is that it binds to the enzyme substrate complex. So competitive bound to free enzyme, this binds to complex. Once you're bound to complex, you have a dead enzyme. And what this does is that it lowers Vmax, but it also lowers Km, which is interesting. But yeah, just remember for uncompetitive, you lower both Vmax and both Km. So I can explain lowering Vmax relatively easily. If you have 100 enzymes, let's say your maximum speed is 100 reactions per second, right? That's Vmax. But this inhibitor binds to the enzyme substrate complex and takes them out of the game. So if I add inhibitor, maybe now it only looks like I have 80 enzymes because 20 of them were bound to my inhibitor. And since I'm not competing at the same site, there's like no way to free that other than just by chance. So now my Vmax apparent is 80 reactions per second because I am now going, now I only have like 80 enzymes that are working. So that's why Vmax lowers. Let's think about Km, right? So let's say that I need 100 substrates. I'm going to keep it super easy. 100 substrates to go my maximum speed. So Km would be 50 if I had 100 enzymes. So one substrate, one reaction. So when I add inhibitor, now I only need 40 substrates to go 1/2 my maximum speed because my speed was lowered. So the amount to go 1/2 my speed is also lowered. So that's why both Vmax and Km are lowered. You can add as much substrate as you want, and you're not going to reverse this. That's different than competitive. Competitive, you could add more substrate and reverse it. If we look at the Lineweaver-Burke plot, a classic view of uncompetitive is parallel lines. So that's how you know you have uncompetitive, if you have parallel lines. As you increase inhibitor, since Vmax will go down, and this is inverse, that means the lines actually go up. Again, it's really hard to think about inverse. It does the opposite of what you naturally think. So when something gets smaller, the inverse of that gets larger. So that's why it goes up and it goes to the left for the Km. It gets bigger. And the alpha constant we have here is called alpha prime. So on uncompetitive, remember, that's always given the prime. And it affects both Km and Vmax. And you get parallel lines. So those are the big takeaways there. So any questions or any clarifications for uncompetitive enzymes? All right. The last type of inhibition we're going to talk about is called mixed, or also you'll find it called non-competitive. Let me just write down what this says. So that's E1. ESI, no reaction. And mixed is weird because it can bind either to the free enzyme or the complex. And because of that, it has two different inhibition constants. It has both Ki, like we saw in competitive, and Ki prime, which we saw in uncompetitive, because it behaves like both. It can bind both. It also has alpha and alpha prime. Remember, alpha is what was in competitive, and alpha prime is what it was found in uncompetitive. So you really want to think of mixed as the two previous inhibitors just combined. That's exactly what it is. And the way to determine mixed on a Lineweaver-Burke is that the lines cross off the axis. And the reason why that is because Vmax always decreases. So as the inhibitor goes up, Vmax decreases. However, Km's weird because it can increase, decrease, or stay the same. And it's all based on what your actual inhibition values are of these alphas. So it can be anywhere like on the x-axis. However, it will always go up on the y-axis. So that means that they're crossing off the axis. And that is our mixed inhibitor there. So any questions about our mixed inhibitor system, like what you're looking for or what it means? All right. So big takeaway. What do I want you to know from what I was just talking about? You should be able to tell me for these three types of inhibitors, how Km and Vmax change. You should know on a Lineweaver-Burke plot what these types of inhibitors look like. You know, if I put the non-inhibited line in the inhibitor, what's my plot's going to look like? And we'll get some practice on this on Wednesday. We should be able to calculate alpha, Ki, and Ki prime. This table, it's a very nice table to study from, as it tells you how everything's going to change with our three types of inhibitors, and also no inhibition. But instead of like jumping into the math problems, because I think that's going to take me like more than 5 minutes to do, I want to give them time. I think for today, we're going to call it here. On Wednesday, we'll finish up these problems, and then we can talk about test 4. Anything you want to know about test 4, I'll answer. If you want me to go over extra things for test 4, I'll do that as well. Or if you wanted to jump into the final to prepare for that, we can also do that too. But I'm guessing you're all going to be concentrating on test 4. So yeah, we'll call that a day here. If you have any questions about anything, you want a tutoring session, whatever, never hesitate to email me. Other than that, I have nothing left for you. So we'll call it a day. Hope you have a good rest of your week, and hopefully see you on Wednesday. Take care, everybody.